Hess's Law, the law of heat summation. That's what today's lesson is going to be on. Now, in the previous chapters, we looked at the idea of using coffee cups as calorimeters, right? So we usually use these with dilute aqueous solutions, right? So if we're trying to dissolve, let's say KCl, in water, right, and try to form, right, or sorry, it should be a solid, and we try to dissolve it in water, and we form our aqueous solutions of our respective ions, we can do something like this using this type of calorimeter. However, there's some reactions, depending on the type of reaction, that either work extremely slow, right, like rusting of iron, or something like any type of combustion. Some combustion reactions, like the combusting of carbon, because it'll form carbon monoxide. We're going to see this reaction in a second, and they're considered pretty much, they require a lot of energy, right? So because they require a lot of energy, one of these calorimeter experiments is not exactly feasible. Plus, one thing we're going to notice with this reaction is that there are two steps to some of these reactions. Some reactions will not go forward in one direction. They will actually have what we call intermediate reactions that are taking place until we get to our final products. Chemists can determine the enthalpy change, right, that delta H, as we've talked about, of any reaction using an important law known as Hess's Law of heat summation. Keyword here in summation, sum, as we're going to see in just a moment. Hess's law states that the enthalpy change of a physical or chemical process depends only on the beginning condition, right, the reactants, and the end conditions, which are your products. So if you've got intermediate reactions that take place in the middle, right? So you might have a reaction, some type of chemical equation that's going to go in one direction, and then the products in that reaction might react with something in the reactants, right, and form a second equation. So what we're going to be looking at is really, well, some multi-step equations that can occur in certain types of reactions. So the enthalpy change is independent of the pathway of the process, as we're going to see in just a second, and the number of intermediate steps in the process. So what we're looking at is really the sum of all the enthalpy changes of all the individual steps that make up this process. So let's look at the following here. Two ways in which carbon can act with oxygen. Carbon can react with oxygen to form carbon monoxide. Now, the carbon monoxide, however, that is formed here in this reaction in the products is going to react with something in the reactants to form a new product. So this is what the reaction is going to look like. So carbon here, as we look at it, because we're combusting carbon, right? We're looking at the delta H, the change of enthalpy based on 1 mole of carbon, is going to go in the following direction. So carbon is going to react with half a mole of oxygen. Again, just for argument's sake, we're going to use fractions, and because this number is based on 1 mole of carbon, of course. Now, we've got this following reaction, but look at one of the products here that we're forming, carbon monoxide gas. Look at this next reaction. So we've got equation 1, now equation 2. Look at this. The carbon monoxide in this system that's going to form, look at what it's reacting with. It's reacting with pretty much one of the reactants from the original equation. So what's going to happen is you're going to have two equations that can be occurring within the same reaction. Right? So two things that can be occurring in the same reaction. Now notice here the change in enthalpy. Right? Look at the amount of heat that's left in terms of this first equation. Right? When carbon reacts with oxygen to form carbon monoxide, it pretty much gives off this amount of energy, this amount of heat. Now, if we look at the second equation, look at this second equation. All of a sudden, we're giving off even more when this second reaction occurs to form carbon dioxide. But now, another reaction that can actually occur is the following. Carbon can also react with oxygen directly to produce carbon dioxide. So all of a sudden, carbon can react with, or 1 mole of carbon can react with 1 mole of oxygen to form carbon dioxide. And look at the amount of heat that is actually given off. It's a greater amount. Now, if we look really carefully with these reactions, this is what we've got. We've got the following 2 reactions that can occur. And then we've got one big one that kind of combines equations 1 and 2. And that's really what we're doing. We're actually going to be combining equations 1 and 2. So what we've got here, oops, I should have kept the 1 and 2 there. I'll keep that right there. Really what we're doing, if you look at this number right here, these 2. Look at these 2 and then compare it with this one. Notice something? Yes, if you look at it really closely, if you add these 2 numbers together, right, you're going to get minus 393.5 kilojoules of energy or heat is going to be released in this combustion reaction. Right? Now, another thing to make note of is the following. Look at what the reactants are. So what we're going to do is we are going to write out our reactants. So we've got carbon in the solid form plus a 1/2 mole of oxygen, gas, plus, and we're gonna add all these together, carbon monoxide, gas, plus another 1/2 mole of oxygen gas. It's going to react to form carbon monoxide gas plus carbon dioxide gas. Now, look at this. So we've got, these are all our reactants. These are all our products. Now, look at what we're going to do. Right? This is what pretty much you'll be doing when dealing with Hess's Law type problems. You are going to be looking for commonalities within the 2 sides. So notice here, both on the reactants and product side, we have carbon monoxide. So we're going to cross these out. We're going to cancel these out. If we look here, right, look at what we're left. We're left with carbon reacting with a 1/2 mole of oxygen plus another 1/2 mole of oxygen to form 1 full mole of oxygen. So we've got carbon reacting with a full mole of oxygen to form carbon dioxide. So really what we've done is we've combined these 2 reactions, right? Because these 2 reactions can actually occur in the system. This will reaction number 1 here and reaction number 2. Or it has the possibility of looking at it in terms of all this. But all this is really what we're looking for. We're actually looking for the combined sum of these 2 reactions. And so that's really what the focus will be with this video. Now, let's look at the enthalpy pathway for that following reaction. Right? So here we had pretty much the combined. This is what we're ultimately going to label as the target. Right? This is the target equation we're going to be looking to achieve. Right? This final step combining all the different intermediate steps. Right? So what we're going to have is we're going to have carbon reacting with oxygen. Right? And notice how this delta H, it's an exothermic. So because this is exothermic, our reactants have a high potential. Right? So in terms of enthalpy, this enthalpy has to drop. And it's going to drop down here, let's say, right? It's going to drop by about minus 393.5 kilojoules. However, if we look at this equation here and we combine them, right? Look at this. We're going to have the 1 carbon and 1/2 mole of this oxygen, right? So we're still here. These are really our reactants. But what's going to happen is we're going to have this intermediate step here, right? So before I can form this CO2 down here, there's another reaction that's occurring in a sub-step. So here, if we look at it, we've got this intermediate reaction that's taking place, and it's taking place with a release of about minus 110.5 kilojoules, right, of heat. And then when this carbon monoxide now reacts with the remaining half, right, of oxygen here, right, it is now going to give up pretty much another, and it's not the scale, of course, minus 283 kilojoules of heat. So now if we look at it, we're combining really this here with this to get what this target change in enthalpy will actually give us. Right? So in terms of graphing it, this is how we would graph it, right? Identify whether or not something is exothermic. So if something is exothermic, you'll have a delta H that is negative. So if you have a delta H that is negative, you know that your reactance is going to be up top. Right? And of course, because it's giving off that energy, right? We're giving off that heat, so to speak. Right? We're going to be dropping down in terms of potential energy. Hess's law allows you to determine the energy of a chemical reaction without directly measuring it. Right? As we've said before, some reactions are very difficult to maintain in a controlled environment. So two ways that we'll use Hess's law pretty much in this video and in a future video is as follows. So in this video, we're going to look at combining chemical equations algebraically, like I showed you guys before. This is what we're going to focus on with today's video. And with the next video, we're going to be looking at using enthalpy, a special class of reactions called formation reactions. And I mentioned that we would look at formation reactions in a future lesson, and I talked about this in previous videos. Now, in terms of Hess's law can be simplified as follows. So the change in enthalpy of our target, right? This is the final equation that we have, our initial reactants and our final products. And it's going to equal to the sum of the change in enthalpy based on whatever is considered known. Right? So we're going to have our known equations. So if we've got the change in enthalpy for the first reaction, plus the change in enthalpy for the second, right? Plus the change in enthalpy for the third, plus so on and so on. And that's how it really goes in terms of getting the target. So the target change in enthalpy is equal to all the changes in enthalpy of all our known equations. Combining chemical equations algebraically. One way to use Hess's law to calculate the enthalpy change of a reaction is to add the equations for the reactions with known enthalpy changes so that their net result is the reaction you are interested in. Right? So what you're going to look at is really what are the two steps that will result to getting the final product. Right? So we've got these two reactants, and we're going to come up with this as our final product, right? So, but we're going to write out a target equation as such, right? So this is really what it's going to look like. So you're going to get, your initial steps, right? Your equation 1 and 2, as we've shown, and I've shown this one just moments ago. And really, what we were doing is trying to combine, as we did, all our reactants, and then combine all our products, and then figure out which ones ended up canceling out. And using this step, right, as we said before, right, the change in enthalpy based on the target, right? So this bottom equation, oh, I cannot write on my tablet today, it's acting up. Target is equal to the sum of all the enthalpy changes of our known, right? And our knowns, we've got two equations that are representing our known, right? Equation 1 and equation 2. So what we're doing is we are taking this value here and we are adding it to this value here, right? To give us the value that we got just moments ago when we were adding these two questions as follows: minus 393.5 kilojoules. Okay, so the change in enthalpy based on this target reaction or target equation is as follows. let's look at a sample problem here. Determine the enthalpy change of the unknown reaction. So here we have equation 1 and equation number 2. And this equation number 3 is really our target, right? So what we want to do is we want to look for these products, and reactants. So look at in the final. Look at where we've got H2O2, hydrogen peroxide. We've got it here in the reactant side. So of course we want to make sure that it's also in line, because what's going to happen with some of these, and this is a nice and simple one. These are some of the more simpler of the questions. Sometimes you might have to rearrange these equations, and as I'm going to show you with one of the later, or the next sample problem. Anyhow, let's look at here, this other product, or sorry, yeah, final product, water. And look, we've got water here. Again, also on the product side. Now, we've got oxygen here on the product side, but we've got oxygen on this product side. We've got oxygen on this reactant side. So what we're going to do now is, let's delete some of this so we can see it. What we're going to do is combine, really, our reactants together, right? Because, well, they look like they're in line with what our target equation looks like. So let's line them up. Let's rewrite them. And we're going to get as follows. H2O2 liquid plus hydrogen gas plus a half a mole of oxygen gas is going to react. And let's put together our products. Hydrogen gas plus oxygen gas plus water. Now, so we've combined all our reactants, we've combined all our products. Again, to do this, make sure that your target equation have these same reactants on the reactant side, these same products on the product side. So now, let's look for commonalities between the reactants and products. So if you look here, both on the products and reactant side, we have hydrogen gas. So hydrogen gas cancel out. Now we've got half a mole of oxygen on this side, a full mole on this side. So what are we going to do? We're going to cancel out half a mole on this side, and we're going to cancel out half a mole on this side. So all of a sudden, our final reaction is going to look as follows. H2O2 liquid, no other reactants, is going to decompose into half a mole of oxygen plus water. Right? So now, again, if you look at this equation, our target equation, as we said, right, it doesn't really matter, even though I wrote oxygen before I wrote the water, it doesn't really matter. These are still the products. So what we did really was we combined these two, the reactants and the products. So what we're going to do is we are going to add now this. So we're going to, our target, right, our change in enthalpy of our target is really, we're going to add 188 kilojoules plus this negative 286 kilojoules. And just to kind of reiterate some basic math skills, right, this positive minus, right, positive negative is going to form a negative. So what we're going to do is we're going to subtract 188 kilojoules from 286 kilojoules, and we will end up with a change in enthalpy for this, right? So this change in enthalpy is actually going to equal to minus 98 kilojoules. So negative 98 kilojoules, right? So what we did was we added these two together because, again, we don't just right away automatically do this. We want to make sure that if we combine all our reactants together, all our products together, and we start canceling out, right, common entities between, common compounds between the reactants and products, and if we want to make sure that we're left with the same products and reactants as our target equation. Let us look at these same two equations, right, in a graph form, right, showing their change in enthalpy, showing their potential energy. So we've got the target here at the bottom, right? That was the one we were trying to find. And if we look at the first equation, we've got hydrogen peroxide decomposes into hydrogen gas and oxygen gas. And if we look at the change in enthalpy, right, we notice that it's a positive value. So we know that it is endothermic. So we know that hydrogen peroxide will have a lower potential energy than the actual products. So let's put that on a graph, right? We'll put it right in the middle, right? Because all of a sudden then we're going to see this decrease as we're going to show in just a second. You'll understand why in a second. So we've got change in enthalpy, right? And because it's endothermic, it is absorbing heat, right? So it's going to absorb heat to and then form the following product. So all of a sudden here, we are going to have this change in enthalpy, right? That is a positive value, right? Positive value, it will equal to 188 kilojoules. Now, we've got these products, and these products now will pretty much reform once again to form water. But now notice when these two, right, form, right, they come together to form water, look at that release of energy. So this reaction, this actual equation number 2 is actually exothermic. Right? So all of a sudden there is a greater potential energy. Why? Because it absorbed all this extra energy. But there's a greater potential now. And then once it forms the water, it is going to give off a great deal of energy, right? Great deal of heat. So it's going to give up change in enthalpy, that is minus 286 kilojoules. But now if we look at this target equation, we are starting off with hydrogen peroxide and we're ending off with water and oxygen. So in actuality, this is where the target is going. This target is going from here down to here. So what we're looking at is, let's look at this new change in enthalpy. So this new change in enthalpy is the sum of these two together. So if we add these two together, we are going to get that change in enthalpy for our target that is equal to minus 98 kilojoules. So we know this overall target equation is considered also exothermic, as it's giving off all this heat, but it's not giving off as much heat from here to here as it does from here to here. Manipulating equations to use Hess's law. Now, sometimes, right, the equations that I've shown you real simple. Everything worked out, right? You combine all your reactants, combine all your products, right? So, but sometimes we need to make changes, right, to our initial equations, right? Because in actuality, we are trying to reach our target equation, right? Sometimes we might have to do one of two things. We might need to reverse an equation. So all of a sudden, our target equation is going to have a reactant that is in fact not found on any of the reactant side, and it'll actually be found in one of the product side of one of the initial reactions. You'll understand what I mean. So what we're looking at is, if we have an equation that is going in a certain direction, right? So if we look at something like the decomposition of hydrogen peroxide, as we just saw. Right? So hydrogen peroxide decomposes into hydrogen gas plus oxygen gas, and it's going to have a change in enthalpy that is 188 kilojoules. So 108, and this is supposed to be kilojoules, so decipher that in any which way you may. So what we're talking about by the idea of the reactants, by switching this, sometimes, right, by reversing a reaction, we want the products become reactants and the reactants become products. What we're going to do is maybe we want hydrogen gas and oxygen gas over on this side. So what we might have to do is rewrite the equation, but in the reverse order, where the products of going in one direction become the reactants going in another direction. But now if we do this reverse, all of a sudden we also need to change our change in enthalpy to accommodate the reverse. So going in this direction, we are going to have an endothermic reaction. But if we go in the opposite direction, we're going to have an exothermic. So it'd be minus 188 kilojoules. So the reverse of this equation is going to be the opposite, so the negative. Some books will tell you to multiply it by -1. I just like to say, well, if it's positive one way, just make it negative the other, right? That's it. Or if it starts off at negative, you make it positive, right? And you'll understand more when we get to this sample problem. And the last step is you might need to multiply each coefficient in an equation by the same integer or fraction, to make the equation suffice, right? Because all of a sudden, you might be dealing with initial equations that are dealing with 1 mole of a substance. But if you look at your target might actually increase by 3 moles, right? So in other words, your change in enthalpy will also change by a factor of 3. And again, you'll understand what I mean when we deal with this next sample problem. A sample problem here, and this kind of puts into perspective really all those steps, the idea of manipulating your equations to make them work, right? So here we have the following. We're going to be reacting iron 3 oxide with carbon monoxide to give us the following chemical equation as follows. Fe2O3 with plus 3 moles of carbon monoxide to form 3 moles of carbon dioxide gas and 2 moles of iron. So determine the enthalpy change of this reaction given the following equations and their enthalpy changes. So this is the information that we've been given. We've been given really some of these types of reactions. We've got carbon monoxide gas plus a half a mole of oxygen gas to form 1 mole carbon dioxide, and it's exothermic, and it will give away this amount of heat. If we combine iron with oxygen, it will form the iron 3 oxide. Now, here we have really our target equation. We want to be able to combine all our reactants and combine all our products and start to cancel out, right? So what we want to do is make sure that whatever the reactants are match the reactants here. So let's look at equation 1. So we've got equation 1 and equation number 2. So in equation 1, we've got carbon monoxide gas, carbon monoxide gas. So yes, we know that this reactant is this reactant. Reacts with oxygen. There's no oxygen on this reactant side. There's no oxygen on this product side. So we know odds are this oxygen, and it's going to give off this amount of heat. And we know it's exothermic because of the negative value. Now let's look at equation 2 now. We've got iron on the reactant side. Look at where iron is here. Iron is on the product side. So reactant on this side, product on this side. We want this equation, actually, and another thing that we're going to notice, as we said, oxygen is neither direction, so odds are oxygen will probably end up canceling out. And look at what the product here is, iron 2 oxide, which happens to be the reactant in our target. So what we want is, we want our reactants to match the reactants and products of our target. So equation 1 is as is, right? And I'm going to not put the states just to make things hopefully a little bit neater. But when you're working yours out, please include the states. So delta H is equal to minus 283 kilojoules. Now, this is our first equation, right? As we said, equation 1 so far matches now, but the only thing is equation 2. This reactant is a product in our target. So we want to switch it because also this product here is the reactant of the target. So what we're going to do is we are going to want the equation to go in this direction. So what are we going to do? We are going to rewrite equation number 2, and we're going to rewrite it backwards. So we're going to start off with our products and Fe2O3. So what we're going to do is, remember, this is a equation 2 going in this direction is a synthesis reaction, a formation reaction. We're going to go in the opposite direction, which is a decomposition. So we are going to decompose iron 3 oxide into 2 moles of iron plus 3/2 moles of oxygen. But now notice what I'm going to do here. Our change in enthalpy is equal to 824.2 kilojoules. Going in this direction, it's exothermic. Going in that direction, it's the opposite. It's endothermic. So it will reverse the charge, right? So it will go from negative to a positive, or from a positive to a negative. Some books will tell you to multiply it by -1. I just like to tell people, just switch the signs, right? If it's negative, make it positive. If it's positive, make it negative when you're reversing it. Now, let's look at it. Let's look at our products, sorry, at our reactants. So we've got Fe, and we've got CO and oxygen. Those are our products, right? Look at it. And these here are these are our reactants. These are our products. So what we're going to do is we are going to rewrite this using all these steps. So now we've got, another thing to keep in mind is if we look at, actually before I actually combine them, I cannot combine them just yet because there's one more step that I need to keep in mind. Actually, you know what? Let's do it. We're going to do that step last. So what we're going to do is we're going to combine them, our reactants. So we've got CO plus 1/2 O2, right? And we're going to add it. And I'm going to change the color, plus Fe2O3. So I'm going to have purple to represent equation 1 and blue to represent equation 2. And I'm going to form my products, which are as follows: CO2 plus 2Fe plus 3/2 of oxygen. Now, if we look at this equation, we've got 1 mole of carbon monoxide, 3 moles of carbon monoxide. We've got 3 moles of carbon dioxide. So what we have to do to this equation here, equation 1, is we need to multiply it by a coefficient of 3. So we're going to multiply all these terms by 3. So 3 times 1 becomes actually, let me delete some of this here. Okay. So 3 times 1/2 becomes 3/2. And we're going to multiply this by 3. So now all of a sudden I'm going to incorporate 3 moles of carbon monoxide, 3/2 moles of oxygen, and 3 moles of carbon dioxide. Now, not only do I multiply those by 3, but I have to multiply also this delta H by 3. Because remember the equation, delta H is equal to N delta H of the reaction, right? So if the mole number changes, so will the change in enthalpy. The change in enthalpy will also change, right, by however many moles. So because we multiplied it by 3, this delta H now is going to become the following. So let me just grab my calculator here. So we're going to multiply 283, and we're going to multiply it by 3 to give us by minus 849 kilojoules. Right, so this first reaction is going to be as follows, and this reaction is as follows. So now let's go and start canceling out common compounds. So we've got CO, and only CO appears. We've got 3 half moles of oxygen on both sides, and they cancel out. We've got Fe2O3, which doesn't cancel out. We've got 3 CO2, and we've got 2 Fe. So in actuality, our end result is really our actual equation. So we've got 3 moles of CO plus 1 mole of Fe2O3 to produce 3 moles of CO2 plus 2 moles of Fe. Exactly like our target up here. So if we look at our target equation, we just got our target equation by adding the 2 types of reactions. Now, to find the actual change in enthalpy of this reaction, well, we're going to take this value here and we are going to add it to this value here to give me what is really the change in enthalpy of this actual equation. And the change in enthalpy of this overall target is as follows. When we add these two, minus 849 plus 824.2 kilojoules, we are going to get a value of minus 24.8 kilojoules. So in actuality, this target equation is actually an exothermic reaction. So when this iron 3 oxide reacts with carbon monoxide, it is going to give off this amount of heat when it forms these 2 products. So a few things to be careful of. Rearrange your equation. Right? So we rearrange your equation so your reactants, right? Your reactants and products match the reactants and products of your target. And then make sure that the moles also match the number of moles in your target. But not only are you multiplying all the terms in your equation by that mole number, you're also multiplying your delta H by that value as well.